these trig functions, right? That's the last, is that the last? No. We didn't start chapter 3 yet. Perfect. Yes, that's right. Okay. So you guys probably looked at worksheet 1 and 2. Did you guys have questions there about from either of those yet? Gabby? From worksheet 2 here?
Yeah.
Okay. Got flies in the room. It's a weird day already. Okay. So it says to just describe the transformation for the graph where the parent function is x squared. So if I look at this, I'm looking for my values for A, H, and K, where they look like this. So the place I have to be careful is over here. So I'm going to start by factoring out that -3. So remember when we factor out something from a like a greatest common factor like this, we're dividing. So -3x divided by -3 is x. And then +2 divided by -3 is going to be -2/3. So here my A is -4. My C, well, I see that 1 over C is -3. So C is going to be the reciprocal of that, so -1/3. H is going to be 2/3. And K is going to be -1/2. So I can say since the C is negative, we're going to have a reflection across the y-axis. Since the magnitude of C is less than 1, we're going to have a horizontal shrink by a factor of 1/3. Since the A is negative, we're going to have a reflection across the x-axis. And since the magnitude of A is bigger than 1, we're going to have a vertical stretch by a factor of 4. Since the H value is positive, we're going to go right 2/3 of a unit. And since the K value is negative, we're going to be going down 1/2 a unit. Bless you. You're welcome. We okay there? Emilio?
On a test or quiz, would you be given the
Shoot, I don't remember what we did in the past. If you're, let me look real quick. Maybe I have that handy where I can tell you. I'm going to tell you this, that comes up over and over and over again, and you'd probably be well served kind of memorizing that.
Okay.
It's not being so easy to find right now. Let's look at that. If it's here, it's there. So yeah, I would give you that with the it would be the function form, would be the one with the f in it rather than the x squared, where it's generic to any function. But yeah, I give that to you. Was a totally fair question. So again, with these problems here, not a lot to it from an algebraic standpoint, like not a lot of computation going on, right? It's mostly just kind of applying these rules that we kind of went through last time in class. Okay. Anybody else before we start chapter 3? No? Okie dokie. Let's do that then. So in chapter 3, what we're going to be doing is we're going to be talking about how to graph the sine and cosine function and about how to write the equations for graphs of sine and cosine functions. So we're going to start by doing just a little bit of a recap here. So again, remember from last time, if I have some parent function, I can transform that parent function like this. So I can either say, okay, these are the transformations I want to do, and I can use that formula there to transform my parent function to get a new equation. Right? That was something we did. Or I can say, okay, this is the equation of my transformed function. Like, what happened? So I can decode from it like, okay, it was reflected and stretched and shifted up or down or whatever. Everybody's okay with that? So this was like the algebraic representation for that transformation. We also had like the graphical representation where my parent function, this time I'm just talking about transforming a point. But I can take any point from my parent function and turn it into the transformed function by kind of following that map there that we've drawn. So those are the two big ideas that we talked about last time. I'm just kind of recapping them here because we'll use these today when we start talking about sine and cosine functions and how to go about graphing them and whatnot. Okay? Okay. So let's do a little bit of an information dump here. So I'm going to build like a little table here. This table is going to have, let's see, 4 columns and a whole bunch of rows. I'm going to go and write the first column here, which is just a bunch of titles. Some of these titles are things that we should already be pretty familiar with and comfortable because we talked about them in the last chapter. Or, I'm sorry, the chapter 1. And some of them are new to this chapter, and the ones that are new, I will, we'll talk about what they mean here in a moment. So for example, like amplitude is something we probably haven't heard before. Or midline. Or period. Or frequency. Okay, so I'm going to pause here a little bit and let everybody kind of get caught up that's following along. So I have 4 columns here. The first column is just all titles. The second column is f of x equals sine. The next one is f of x equals cosine. And the third one, I just have the general transformation of a sine or a cosine function. So a sine of 1 over c times the quantity x minus h plus k. And then the same thing there with cosine instead of sine. Okay, so let's talk about the domain here to start with. So if you remember from last chapter, we had the big idea from last chapter is that we took our definition for sine, cosine, tangent, etc., from being things that were linked to the angle measures inside of a right triangle, and we extended that definition to make sine and cosine and tangent related to the coordinates of a point on the unit circle, right? So we defined this new way of describing an angle called the standard position angle that allowed us to describe angles of any size, positive or negative, as big as you want or as small as you wanted. And we extended those definitions of sine, cosine, and tangent so that wherever the terminal side of that standard position angle intersects the unit circle, we can use that point of intersection to find the values for sine, cosine, and tangent. So if I'm talking about sine and cosine, which we are here, the input to the sine function is going to be an angle measure, and the output is going to be the y-coordinate from the unit circle where the terminal side intersects the unit circle, right? So for example, if I had like a 90-degree angle, the output would be 1, right? So the input is the angle measure, and the output is that y-coordinate from the unit circle. Does that sound good to everybody, Lily?
The input is the first steps, right? So can you just repeat that?
Yeah, so for a sine or cosine function, the input is the angle measure, and the output is going to be one of the coordinates from the unit circle. In the case if we're talking about sine, the input could be 90 degrees, and then the output for that would be the y-coordinate there at 90 degrees, which is 1 in this case. So the inputs are angle measures, right? Everybody good with that? So we can make an angle measure as big or as small as we want, right? That was one of the big results from last chapter. Everybody's okay with that? Regardless of how I draw my angle, is the terminal side of it, is that going to intersect the unit circle? Yeah, right? There's no way I can draw an angle, like there's my initial side. The terminal side has to intersect the unit circle somewhere, right? No matter how I draw that, it's got to intersect. Everybody agree? So what that tells me is that every input I can come up with to sine has an output. Everybody's okay with that? So the domain then for sine has to be all real numbers. And we'll describe that with our set notation, or interval notation, I guess. Everybody's okay with that? Because again, the domain is your set of inputs. The range is the set of outputs. So the outputs for us for sine are tied to the y-coordinate on the unit circle. So what's the smallest y-coordinate on the unit circle? Well, it's here at -1. Everybody agree? The biggest y-coordinate on the unit circle is +1. And every other y value in between is covered because there's a point on the unit circle corresponding to every other y-coordinate between -1 and +1. So the range for sine, the possible outputs, are going to be between -1 and +1. Notice that I'm using the brackets here because sine can actually have the values of -1 and +1. Those are actual outputs that sine can have, so I need to use the bracket to indicate that those are values that are also in my set of input or outputs, excuse me. Everybody's okay with that idea? Okay. So what is the graph of sine going to look like? Well, let me just generate that real quick for us. And then we'll talk about how I come up with this. So this is what my graph of sine is going to look like. Now, how am I getting something like this? Well, I'm just plotting points using my unit circle. So the x-coordinate is my input, so that's going to be an angle measure. And the y-coordinate is my output. In the case of sine, that's going to be the y-coordinate from the unit circle. So notice the x-axis here is all in terms of pi. Typically, when we graph sine or cosine functions, we use radians as our angle measure. The reason is, if I'm going to make a graph and I'm going to draw an x-axis with some tick marks, graphing all the way through 360 is a heck of a lot of tick marks, as opposed to graphing to 2 pi where, well, 2 pi is a little bit more than 6. That's a lot less to draw. Is everybody okay with that? So typically when we're graphing, the angle measures we're going to be using are in radians. That's okay, right? We've dealt with going back and forth between degrees and radians a fair bit already. Okay, so let's say we wanted to graph this or generate this graph that I'm just showing you. So my input is going to be 0 radians, and the output there for sine would be 0. So I would plot the point 0, 0. Then say maybe we do 90, or I'm sorry, pi over 2 is my input, and 1 would be my output. So there's that point. And then say pi, and then 0 would be the output. So there's that point. And then 3 pi over 2 and -1. That would be this point. And then we're back to here at 2 pi, so 0 again. And I could keep kind of going around my unit circle. And I'm not picking using all the points from the unit circle. I'm just kind of using every so often to give me an idea of what's going on there. Of course. Is everybody okay with kind of how I've generated that graph? We're not going to ask you to generate by hand from the unit circle, but I just want to make sure I'm showing you guys the connection between what we did last chapter and what the graph of this thing is kind of looking like. Emilio?
I'm a little confused as to how you got the points. Like the actual.
Right. So for example here, the angle measure is 0 radians, and the value for sine is 0. So the x-axis is the angle measure, and the y-axis is the value for sine. So the angle measure there was 0 radians, and the output is 0 for sine, so that's the 0.00. Does that feel okay?
Yeah.
Again, because that's the input is the x-axis, right? The things that we're inputting into sine are angle measures. And the output is the y-coordinate from the unit circle. That's our value for sine. Everybody so far so good? Okay. So let's look at this picture now. I think the next thing on my list is symmetry. So notice how like this part of the graph looks kind of like a reflection of that part of the graph. You guys see that? Now, one of the types of symmetry we talked about in chapter 1, this was characteristic of. It's the odd symmetry. So is where the graph looks kind of like a reflection when it's kitty corner with the quadrants. That is odd symmetry. So continuity is next. So remember we talked about discontinuities in chapter 1, things like asymptotes or like breaks in the graph or jumps in the graph. Can that happen here with what we've drawn? Do you see any asymptotes? Do you see any breaks, any jumps? No. So again, sine is everywhere continuous, which makes sense, right? Because we're pulling the outputs for sine from the unit circle. All those y-coordinates are all going to be right next to each other, right? There's no jumps or gaps in the unit circle. And all the inputs are angle measures that could all be right next to each other, right? You give me an angle measure, I can give you one that's like real darn close to it, like infinitely close to it. So, okay, the last 4 are going to be kind of visual descriptors for these graphs. So we're actually going to start by talking about the midline first. The midline for one of these graphs is the line that divides the graph into, so that basically in half. So like the area bounded between the graph and the midline is like the same as the area bounded between the graph and under the midline. Does everybody kind of see that? It basically just divides it in half. So in our case, for sine, that midline is the x-axis, which is the line y equals 0. Oops. The amplitude is the distance between a extreme point, so a maximum or minimum, and the midline. So in this case, that distance is 1. Everybody okay with that? The vertical distance I'm talking. You could also think about it as like half of the distance between extreme points, right? Between a max and a min. So that distance between the max and the min is 2. Half of that should be the amplitude, which is, again, 1. Is everybody okay with that idea? So again, I'm not going to give like a verbal description of these things. I'm just going to kind of describe what they are from the picture, because that's really what I need you to be able to do, is to look at the picture and be able to kind of identify these things, right? So we're not going to go bananas and like write out a really thorough written description because it's not really going to be very useful for us. Okay. So when we look at a graph like this, notice how it's going like up and down and up and down and up and down, and it's repeating itself over and over and over again. That type of graph is called periodic. And if we look at this graph, I notice that like, hey, if I start here, I have like an up hump and then a down hump, and then it starts over again with a new up hump and a new down hump. Everybody see that? So like these repeating segments here are called periods. So for example, that purple section is one period. It's one of these segments that like repeated over and over and over again creates the graph. You guys kind of see that? So when we talk about the period, it's the length of one of those segments. And when I say length, I mean like the horizontal length. So this one starts at -2 pi and ended at 0. So the length for that is just 2 pi. And the frequency then is related to the period. We define the frequency as like the number of periods per 1 unit. So by definition, the frequency is just going to be the reciprocal of the period. So always is just going to be the reciprocal. Let's now do the same thing for cosine, but we'll go a little bit quicker. Of course. Okay, so the graph for cosine, we would generate the same way, except the outputs for cosine are going to come from the x-coordinates on the unit circle. But otherwise, we generate the graph the same way. So if I look at the graph of cosine and sine, they're almost identical, right? They're not quite identical, but the shape is almost exactly the same. It just looks like it's been moved over a little bit. You guys agree with that? So guess what that means for our table back there? Almost everything is going to be the same as sine. The only thing that's going to be different is the symmetry. Notice here that it's like a mirror image of itself across the y-axis. That was even symmetry. Oh, goodness gracious. But everything else is going to be the same as sine. Okay with that idea? Now let's think about these transformations, right? Last time we talked, we identified 3 types of transformations that we can do. We can do reflections, stretches and shrinks, also called dilations, and then translations, like shifting things left or right or up or down. If I do any of those, can any of those create a discontinuity? Can I tear a hole in my graph, or is it going to create a vertical asymptote or something? No, right? We're just stretching. That can't hurt anything. We're just flipping over the X or flipping over the Y. That can't hurt anything. Or picking it up and moving it up or down or left or right. That can't hurt anything. So the domain for these transformations is still going to be all real numbers. And the continuity is still going to be everywhere. Everybody's okay with that? Okay. So let's talk then about the range. Can doing one of these transformations affect the range? Yes. What kind of transformation might affect the range? In what direction? Vertical or horizontal? Vertical is correct. So like if it gets taller, if I stretch vertically, that's going to make the outputs, the y coordinates, change. So the range should change, right? Or if I shrinked it and they got smaller, again, it would make the y coordinates change. Good. There's another transformation that can also affect the range. So we have vertical stretches and shrinks. What else could affect the range? It's a translation up or down, right? If I pick the graph up and I move it up, then all the y coordinates got bigger, right? Or if I picked the graph up and I moved it down, all the y coordinates got smaller. Everybody's okay with that idea? So if we think about this, we remember that the A controls the vertical stretches and shrinks, and the K controls the shift up and down. Everybody remember that? So notice when we look at the map, the A is multiplicative. It's being multiplied to the y coordinate. And the K is additive. It's being added to the y coordinate. So the range before was -1. So we're going to have K, which is added, minus the absolute value of A, to K plus A. So the -1 got multiplied to the A, and then we added the K to it. I just wrote it with a subtraction symbol rather than a negative A plus K. I just wrote it as K minus A. Is that okay? It's a lot of letters that I just said with the OK in there. It's probably not necessary. Again, notice the brackets are still there. Now let's talk about the symmetry. But let's not, right? If I do one of these translations, remember the symmetry is related to whether it looks like a reflection at the origin. If I do any kind of shifting, I might ruin that symmetry and might be gone entirely, right? And in fact, it's not easy to predict when it be maintained or whatever. We're not going to worry about it. Yes, sir. Of course. Next up is the amplitude. Remember, that was the distance from the midline to the highest or lowest point on the graph, right? Can a transformation change the amplitude? Yes. What type of transformation is going to change that amplitude? Very good. Vertical stretch or shrink. Remember, that's controlled by the A, and it's multiplicative. So the amplitude was 1 before. Now it's going to be A. Notice that I'm writing these as absolute value A's. Remember that A can be positive or negative. But the amplitude is a distance. That's why we just stuck the absolute value around it. Everybody okay with that? Okay. The next thing is the midline. So can the midline be changed from a transformation? Can. So suppose we have this scenario, right? Say our graph has the midline at y equals 0, and I pick it up and I move it up, right? Has the midline changed? Definitely has, right? The k is what's going to change it because that controls the shifting up and down. Remember, the k is additive. So we had y equals 0. When I add k to that, I just have y equals k. Everybody's okay with that? That's fairly easy. The last, we have 2 more. We have to talk about the period next. Can that change? Remember, the period was like the horizontal distance for one cycle. Can that change? Okay, good. What kind of transformation would change that? Horizontal stretch or shrink, which is controlled by the C, which, if we go back and we look, is multiplicative, right? It's multiplying to the x. So our old period was 2 pi. So our new period is going to be 2 pi times the absolute value of c. Notice I'm putting the absolute values on there again because the c can be positive or negative, but the period is a distance, it's a length, so I just need to make sure it's positive. And then the frequency is always going to be the reciprocal of the period, so I'll just write that as 1 over 2 pi absolute value c. Okay with that idea? All right. So let's say we have an example here. Let's say we have y equals 3 sine 1/2 x minus 3 pi minus 2. And let's say we want to basically describe all the things going on in the table for this. So we'll do the domain and range, and amplitudes, midline, period, and frequency. Okay? To do that, really I just need to find the values for A, C, H, and K. And then I can just kind of fill them into the little formulas we developed from our table. So, again, my general transformation for the sine function looks like this. Again, the place where I have to be careful is making sure the inside parts look the same. Notice that they don't, right? So I'd want to start by factoring out a 1/2. So 1/2 x divided by 1/2 is x. 3 pi divided by 1/2 is the same thing as 3 pi times its reciprocal. So 2. 3 pi times 2 is 6 pi. Is everybody okay with that? Okay. So my A is 3, my C is 2, my H is 6 pi, and my K is -2. So the domain Well, that's easy. It's always going to be all real numbers for all sine and cosine functions. The range, well, I go over to my table. That's k minus the absolute value of a, comma, k plus the absolute value of a. In our situation, k is -2 and a is 3. So that's going to go from -5 to +1. Everybody okay there? Just plug the stuff into my formula, right? Amplitude, that was just the absolute value of a. So the absolute value of 3 is just 3. The midline was y equals k. So that's going to be y equals -2, since k is -2 in this case. So far, so good, everybody? The period is 2 pi times the absolute value of c. In this case, my c is 2. So that's going to just give me 4 pi for my period. And my frequency is always the reciprocal of my period. So 1 over 4 pi. You guys feel good about doing something like that? Not so bad, right? We're just using the formulas. The formulas themselves were a little bit tricky to come up with, but once we have them, like, they're easy to use. They're very simple. Again, the hardest part is probably making sure that you factor the inside of your sine or cosine function to make sure you get the right values for a, c, h, and k. Is remembering to do that. So far, so good? Okay. So we've talked now just about the functions themselves and some of the attributes. Let's talk about actual graphing. So let's talk about going from the equation to the graph. Now we remember to graph transformations, we use this map. The question that we're left with is, what points from the parent function do I want to use? Well, I'm just going to give them to you. So if you're like an ancient math teacher that's been doing this for seems like hundreds of years, you have these things memorized. My expectation is that you, as a student seeing this for the first time, would not memorize these. This would be something that I would give to you. So let's do an example here together. Let's say we want to graph 1/2 sine of 2x minus pi minus 1. That's what I'm looking for. So the first thing I'm going to do is I'm going to start by identifying my values for A, C, H, and K. So factoring the inside, 2x divided by 2 is x. Pi divided by 2 is pi. So my A is 1/2. My C is 1/2. My H is pi over 2. And my K is -1. So far, so good? Lily? Correct.
Okay.
Yeah. I guess I should put a y equals here. Sorry about that. But yes, yeah, I just have omitted. We've done it enough times now that I'm just going to start writing the thing underneath it that I'm trying to make it to look like. Is that okay? Okay. And fair question. If it's like, okay, why you did that again because, yes.
Wait, why is the C 1/2?
Remember that 2 is going to be 1 over C, right? So it's the C is always the reciprocal of whatever that coefficient is. Now that I have this, I can write my transformation map. So I have Cx plus H, and then AY plus K. Because we're graphing a sine function, I'm going to use my key points from sine that I just wrote down above a moment ago. So I'm just kind of copying these down. Okay. And now to change these into my transform points, I'm just going to be plugging in the x and y's into that map that I wrote above. You guys kind of see what I'm doing there with plugging these numbers in? Right, I'm just plugging the x in for the x and the y into the y. Right? Is that cool? So I'm going to stop writing down all the work. Is that okay with you guys? Oops. Help if I wrote the right thing here, though. This is 3/4 pi. Yikes! Mr. Kulak, yikes! Tyler. Of course. Okay. So let's go ahead and plot our points now, and we'll start trying to draw our graph. So the grid that I've put up here is the same kind of looking grid that you'll have on your worksheet. Just so it looks the same. So notice the x-axis, each of the grid lines is basically half a pi. So this is like half a pi, 1 pi, 1.5, 2, etc. So my first point is pi over 2 and -1. Then we have 3/4 pi and negative a half. So here's a half a pi and here's 1 pi. So like halfway in between should be 3/4. And we have pi negative 1. And then 5 pi over 4 is 1 1/4, and then negative 3 over 2. And then 3 pi over 2, which is here, and then negative 1. Everybody's okay with that? So this is like my little up-down. That's my one period that I'm graphing. By finding the points anyways. From here, I am going to ask that you guys fill in the rest of the space, but I don't need you to generate points to do this. All I want you to do is kind of follow the pattern of what we've established before. So if I continue going, I should have something here, and then here, here, and just kind of following that pattern, filling in the rest of the space. And same thing over here. You guys feel okay doing that? Or we're just extending the pattern? That's the nice part about these periodic graphs, is you can generate a whole lot of it with just a few points, right? And when I'm looking at your pictures, again, I don't need to see labels for these points. The extension, all I want to do is see a point where the point's supposed to go, and then the curve that kind of goes through it. I don't need to see any labels. Ms. Garcia.
Monaco and Alex. Okay. So 8 cards. So when did you start your second?
So Domenico and Alex.
Let me check my list, because you're supposed to have 3 when you hit 7, but I don't know when you hit 1. Monaco, can you wake up? I'll check it this hour and then we have to keep it.
Okay. What do you guys think? Again, not too bad, right? It's pretty numeric, right? All we have to do is really use the map, calculate our new points, plot our new points, and draw our graph. We might have to do a little extension one way or the other, but that's not the end of the world. This is where we're stopping, because I think we have a short day for mass. Yeah, that sounds right. So your assignment will be worksheet 3, which is just asking you to do, find the amplitude, midline, period, frequency, and then list the transformations. So like stretched or shrinked, reflected, up or down, left or right, etc. And then draw some graphs. Everybody's cool? Okay. Also worth pointing out, on Wednesday is going to be a work from home day. So I've already made the lesson. It's like 15 minutes or whatever. I'm just walking through an example. And you guys are going to work on worksheet 5 on your own on that day. So my example, there's just like 2 questions really on it. So that will add to the problem set. I think the only thing that we'll have due this week, though, will be worksheets 1 and 2, because we won't have a chance to meet and take questions or anything on the other stuff. So let's just worry about that. Sound okay to you guys? Emilio?
So last week's homework is due this Sunday, and this week's homework is due next Sunday?
Yes. Yeah. So the only thing on the problem set for the 10th is going to be worksheets 1 and 2. For the 17th would be the next one. We'll have worksheets 3 and 4 at least, and then, more stuff possibly. Everybody happy?